Okay, good afternoon. Myself, Anil Kumar, again present with you with this short program, short course on GNSS and its applications. Today is the fourth day, if you recall, and yesterday I talked about GNSS measurement and positioning techniques, and today I am taking a different topic of GNSS as GNSS receivers and GNSS errors. So in first part, I will talk about GNSS receivers, different type of GNSS receivers, and after that I will talk about GNSS errors present in the system. So if you talk about GNSS receivers, starting from geodetic GNSS receivers, here you can see the geodetic GPS receivers are having multi-component. This is a heavy half kg around battery, dry nickel cadmium. This is connected with the receiver. The receiver is connected with a control unit, and it is also connected with antenna. Antenna can be on a tripod, on a pole, or on a 1 meter rod, telescopic rod. So here you can see all the components are separate. It can be this geodetic GPS or GNSS receiver can be single frequency or dual frequency. From outside it looks to be same, but from inside when we see the configuration, we can make it out it is which type of geodetic GPS receivers. Second side we can see the handheld GPS receivers. These geodetic GPS receivers can be used as single frequency or dual frequency, but they are used in a pair as base and rover to improve the accuracy. And the cost of these instruments in a pair, one base and one rover, with single frequency may cost 4 to 6 lakhs. For dual frequency may cost 14 to 20 lakhs, depending upon configuration we are asking. Second side, if you see handheld GPS receiver, it is a small, like nowadays, like a mobile phone device. Here you can see alpha or function keys, then alphanumeric keys, the screen, it can be black and white or colored screen. Then you can see the antenna is projected outside sometimes, and sometimes it is inbuilt. We hardly see the antenna. These devices can run with a single or sometimes 6 pencil cells. These devices may have facility to attach external nickel cadmium dry battery, so that continuously non-stop we can do long observations with these type of handheld GPS receivers. Cost wise, nowadays they can come in 5,000 to 50,000 depending upon configuration we are going for. We can see dedicated models of handheld GPS receiver like from Michelin 315, Michelin Sport Track, then Garmin E-Tracks, Garmin GPS Map 76, quite old model but very rugged. Then we can see more models from Garmin. This is a E-Tracks, Trimble, and Michelin. You can see the antenna is here projected outside. You can see the big display screen, all the information, coordinates, point of observation, setting of machines can be done and can be seen on this screen. Geodetic one, you can see the geodetic can be on a pole which is of 2 meter. This is a survey grade antenna. This is a receiver. This is a control unit, and this is the receiver here. And this is the beacon which is working as a transmitter or receiver to apply the corrections. As I mentioned you in the relative positioning, the beacon is required. So physically you can see survey grade antenna. Here that this is a control unit. Back side on which the control unit is mounted is a receiver having different ports here to connect different devices, and this is the beacon to work as base and rover. So we can mount on a tripod or on a 2 meter pole. Then here you can see antenna, the rover is kept on a 2 meter pole. This is the control unit mounted on a rod, and the battery is on the body which is integrated with the cable. Here you can see the old model of GPS 500 series. This is a control unit, this is a receiver, and this is the beacon which can work as a base and rover. Various makes of geodetic one. This from Leica, what I've shown you. This is from Sokia. Again, survey grid antenna. Antenna is kept mounted on 2-meter pole. This is a receiver, and we can control through a palm top. We can give complete all the commands to this machine through a palm top. This is the Trimble model antenna cum receiver, which is mounted on a 2-meter rod. This is a Bluetooth antenna which is communicating with this data logger. So it is wireless communication. We can work within a range of 10 to 20 or 30 meters, very easily remaining far from the instrument, and we can go on doing observation. Then in some of the dedicated machines, we can see total station as a Leica smart station, and there are some other companies which are manufactured the smart station. Smart station means we can mount the total station, and the top of it we can mount the GNSS receiver. So from GNSS we can get the ground control points that can be fed in the total station to start doing observation with the help of total station. Then there is one more type of GPS receiver called mobile GIS GPS. Previously there were 3 components. There is a palm top, there is a GPS antenna, and there is a software which is allowing you to receive the data from antenna and can be stored in the palm top after observation. But nowadays there are dedicated mobile GIS GPS receivers where everything, software, antenna and the palm top, all 3 are inbuilt, and very ruggedly we can use them to get the data in the form of GIS. Why it is called mobile GIS? Because we can create point layer. If there is a point data, we can collect through GPS. We can collect the data in the form of line, like road network or canal network. And if we have polygons like building area, so building footprints, we can map in the form of polygons like this. And we can make one more layer for polygon. So separately we can make one layer for point, one for a line, and one for polygon. So that's why it's called mobile GIS GPS. So we are capturing the data in the form of GIS through GPS observations. Then you can also see nowadays the very good apps I've already shown in my first lecture, which can run on a smartphone like this MI Redmi I'm using, and here there is a good, very nice GPS chip, which is basically GNSS chip, which can receive the data from Navistar satellites, GLONASS, Galileo, BeiDou, and so forth. And the app is called Mobile Topographer. It can give you accuracy of around 1 meter, as I mentioned in the previous lecture, just using mobile phone app. And to start, you can press this button. So if you do that, you will come to this location. After some time, it is waiting to log the minimum number of satellites. Once the minimum number of satellites are logged, it will start displaying latitude, longitude, altitude from ellipsoidal height, and the altitude from mean sea level. And the accuracy also you can see, and you can see how many satellites has been logged. And if you press this button, you can go for start accurate positioning. So by this accurate positioning, so now you can see the coordinates are displayed. Height from ellipsoid, height from mean sea level, accuracy, and number of satellites logged by the GPS has been displayed. You can see which are the satellites this mobile phone is logging. GPS satellites has been logged, GLONASS has been logged, QZSS, BeiDou, and Galileo has not yet because they are red. But after some time, if the satellites are available, it will log that satellites also. So once you go for accurate positioning, you can get the very accurate coordinates, latitude, longitude, height from ellipsoid, height from mean sea level, accuracy from, it was 66, it is now 37 meters. But if you give more time, this accuracy will come around 1 to 2 meter, and so forth. From here, if you press this button once, and then this button is highlighted, so you can save the points from this. Like here, you may get the point ID 42 is saved. Next point, if you are observing, you can save the 43. So like that, you can go on storing the point data, and by default, it gives the ID. You can change the ID if you want the point ID by your choice. And in the end, if you save the file from this button, so you can save the file as a text file .pts, and by default it creates with respect to the date of that day. If you want to change the file name as per your choice, that is also possible. Coming to further some jargon words to understand about GPS. One is mask angle. I also talked about mask angle in the relative positioning, where we have to fulfill the one condition that base and rover should lock common satellite. So with the help of mask angle, we can take care that the base and rover locks the common satellite. So what this mask angle means, GPS receivers or GNSS receivers, processing software or both may have an option to set a specific mask angle. It is also called cutoff angle. So what does it mean? So here you can see I'm standing here. This is my antenna. So in this antenna, if the mask angle is 10 degree, so any satellite which is below, having elevation angle less than 10 degree, suppose this satellite, it will not be locked. So one advantage is we should not lock the satellites which are having vertical angle close to horizon, because their signal travels maximum to the atmosphere, and due to that large number of atmospheric error or delay are introduced in these type of signals. So one thing is, if we should increase little higher end side mask angle to avoid the atmospheric delay. The second thing we should take care, the mask angle of base, mask angle of rover should be more than the mask angle of base. So here the mask angle of rover remains to be 10 to 15 degree. So the mask angle of rover is around 10 to 12 degree. With this combination, shortly whatever satellites has been logged by the base, from that only you will see the common satellites has been logged by rover. Here you can see very clearly antenna setup, mask angle is 13 degree. That means any satellite having elevation angle less than or equal to 13 degree will not be logged. That's the meaning of mask angle. So this satellite is logged by the GPS receiver or GNSS receiver, but if the satellite is here, its angle is suppose 13 degree, that satellite will not be logged by the GPS receiver. So that's the difference between mask angle and elevation angle. Next is satellite geometry. So satellite geometry basically shows the distribution of satellite in an area where I'm doing observations. So it directly affects the positioning accuracy. If the geometry is good, that means the satellites are distributed, my positioning accuracies are better. So here you can see 4 satellites which are very close and they are making a small tetrahedron volume. So that means here the accuracy in my data will not be good. In this case, they are quite far, and you can see the volume of tetrahedron is more and the p-dot value will be low. So with this, it will indicate the accuracy in my data is very good. The best single point positioning accuracy are achieved when satellite have good spatial distribution in the sky. So we should see that the distribution of satellites should be such that 4 satellites should be at an elevation of 20 degree and far between each other of 19 degree, and 1 satellite should be at the top. So with this ideal combination, we get very high, very good satellite distribution. With this, the accuracy in my data is also very high. It improves. Suboptimal geometry exists when all the satellites are clubbed together in one quadrant of the sky. If in some time all the satellites are in one region in my study area, so the distribution of satellite is not good. In that case, the geometry is not good, and in that case, the accuracy in of my data will decrease. So here you can see all the satellites are clustered to one region. They are not well distributed. You can see the volume of tetrahedron is small. In this case, they are well distributed too far, and you can see the volume of tetrahedron is also very large. So there is one indication here. There are so many parameters. One is p-dot. So if you monitor PDOF, it should be low as possible. Smaller the PDOF value, higher the accuracy in my X, Y, and Z coordinates. Satellite geometry we shows generally with one of the very strong parameter called GDOF, geometrical dilution of precision. This includes the error in X, Y, Z, and time. It gives error in all the 4 parameters, right? Then next error, if we see selective availability and anti-spoofing, that there are 2 terms often associated with GPS or GNSS. One is called selective availability SA, and second is anti-spoofing. So these are very 2 terms closely associated with Navistar satellites. A selective availability means consists of degradation of broadcast orbit. That means the accuracy of the satellites are known, position in space, and dithering of the satellite clocks. That means intentionally they are adding error in the satellite known coordinates as well as in the satellite clock time. Intentionally they are adding error. And anti-spoofing means it is the denial of access of the P code to civilian users. Today still we cannot access the P code from Navistar satellites. Only the US Department of Defense can access the P code. So here coming to now GPS errors, with a dedicated more focus on GPS errors. So before that we'll see some of the terminologies, like the question comes, how accurate is a GPS position? So we can define the accuracy of GPS through 2, we can understand the 2 terminologies. One is precise and second is accuracy. So we may have different combinations. The data can be precise but inaccurate. Data can be accurate but imprecise. Data can be inaccurate. Data can be inaccurate and imprecise. Data can be accurate and precise. So in this case, precision means how close my samples are to the true value, and accuracy means how close my samples are. Sorry, the precision means how close the samples are to its mean value, and accuracy means how close my samples are to the true value. So mean we can calculate and then we can find out all the here 4 samples are very close to each other. That means they are close to the mean. So they are more precise, but you can see they are quite far from the true value somewhere here. So you can see large difference between true value and the mean value. So they are inaccurate. Here you can see all the 4 points, they are very close to the mean, but sorry, the actual true value, but they are very far with respect to mean. So they are accurate but imprecise. Here the points are very far to the true value and the points are very far to its mean value. So that the points are inaccurate and imprecise. In this case, points are very close to each other, so they are precise, and points are very close to the true value, so they are accurate also. So this way we can understand the difference between accuracy and precision. Both are not same, both are different. Accuracy is very close to the mean value, and sorry, accuracy is very close to the true value, and precision is very close to the mean value. So accuracy refers how close an estimate is to the true value, which is unknown. So true value always remain unknown, while precision refers to how close an estimate is to its mean estimate. GPS position vary in accuracy from tens of meters to centimeters. So accuracy from GPS we can achieve from tens of meters to a few centimeters or a few millimeters nowadays, depending upon what kind of GPS receiver we are using and which positioning technique we are using. So based on type of GPS receiver and type of positioning technique we are using, accordingly we can achieve the level of accuracy in my GPS data. So truth is that not everybody needs the very highest accuracy data from the GNSS or GPS. Just as there are many different uses for GPS or GNSS, each use needs a different accuracy. So here you can see there are around 4 level of accuracy, and each level of accuracy require different accuracy. So each level of accuracy has good news and bad news. Before that, we can also see the accuracy levels in general. The heights we get from GPS are about 1.5 times less accurate than the latitude and longitude. So in the GPS, the height is less accurate in comparison to X and Y coordinates, and the deviation of the accuracy of Z with respect to XY is 1.5 times less accurate than the X and Y coordinate. A single point GPS position has a typical accuracy of around 10 meters or so. If we are using single point GPS receivers, the accuracy may be around 10 meters, but nowadays more further improvement in the electronics, we can achieve accuracy of around 5 to 6 meters. The good news is this level of accuracy is very easy to get, and the receiver is fairly inexpensive. So when we want around 6 meters of accuracy, you can just switch on the GPS receiver in the open space, wait for a few minutes, and then you can achieve the accuracy in your data to be of around 6 meters. The bad news, not much bad news here except the accuracy, but it's plenty accurate enough to find out way back to your campsite at the end of a hike. So after a hike, 6 meter accuracy is more than enough to use it for the navigation purpose. Second, differential positioning accuracy. If we are using code, till now I've just talked about the two methods which are using code measurement technique. So if in code measurement also we can have relative positioning. So if we go for relative positioning or differential positioning accuracy, we achieve around 0.5 meter to 5 meters in 2D and 0.8 to 8 meters in 3D. So this 0.8 to 8 meter is the error in height, and 0.5 to 5 meter is a 2D error, that is in X and Y. Good news. So here with the code measurement technique, we are applying differential positioning accuracy, and we can achieve accuracy of 0.5 meter to 5 meter in XY and 0.8 meter to 8 meter in Z. Good news about this accuracy is the GPS receivers and software on the market today are very powerful and fairly easy to use, making this level of accuracy very easy to achieve if you are careful. So the softwares are not so costly, and you can achieve by this method differential positioning on the code measurement technique to achieve accuracy to be around 0.5 meter to 5 meters in XY and 0.8 to 8 meter in Z. So this level of accuracy is sometimes called mapping quality because it is often the desired accuracy to locate features for a geographic information system or for mapping purpose. So this around 1 meter level of accuracy is quite sufficient to locate the features in a GIS layer for mapping purpose. Bad news, this level of accuracy requires either two GPS receivers, one working as a roving receiver and second working as a base receiver. So here, the moment we come to differential positioning, we require minimum 2 GPS units, one base and one rover. Then if we are going for carrier positioning accuracy, then we can achieve accuracy in XY to be of 1 centimeter to 30 centimeter in XY, and in Z we can achieve accuracy of 1.5 centimeter to 45 centimeter for 3D observations. So this is the highest level of accuracy possible using the GPS, and is the technique that land surveyors and engineers generally use. This method is often referred as survey grade GPS mapping. So this type of system gives very high accuracy up to millimeter, but very expensive. So in the carrier positioning technique, we can use some functions like if it is dual frequency GPS receivers, and if you are going for scientific processing of the data, so then we can achieve further from centimeter, we can achieve the accuracy in the data to be of up to millimeter level. But it is very expensive to achieve, but we can do that. Then GPS positioning errors, if you see, positioning error is equal to user equivalent range error multiplied by PDOP. So PDOP is a measure of satellite geometry. So from PDOP, we can measure the position error. GPS position error, we can see further, there is an error due to receiver noise, because receiver is an electronic device. Due to long run, this electronic device may get heated up, and due to that heat, it will start introducing error in the own system. Then multipath, multipath means when we are doing observation close to a building, then this can be a GPS. So it logs the primary signal, and sometimes it logs the secondary signal, which is coming, which is reflected to building, and from there it is reflected back to the antenna. So this is a secondary signal which should not be logged by the GPS receiver. It should log only primary signal directly from the satellite. So that is a multipath. Ionosphere is basically when the signal is coming from the atmosphere, there is a ionosphere layer, which is basically charged particle layer. Charged particle interacts with the signal and they introduce delay. Then there is tropospheric layer. Tropospheric error is one more layer after this ionospheric layer, which is having the dust particles and the moisture, and due to this again it introduces the delay, so we may have the topographic delay also. And after that we are having clock. The satellite clock is giving time. The question comes, how correctly these clocks we are receiving, how correctly the clock time is received at the satellite stage as well as at the GPS receiver location. Then orbit, we are using satellite coordinates as a known coordinates of the satellite. The question comes, how correctly these coordinates has been measured. So overall, you can see the orbital error, how correctly the satellite coordinates has been predicted. The satellite clock time, which is the atomic clock, still it may have error. Ionospheric layer, which is charged particle introducing delay. A tropospheric error, which are introducing the delay due to water and dust particles. Then multipath, I have already explained. Receiver noise, the receiver gets heated up due to long run. It's an electronic device, and after heating, it will start introducing the error in the data. Then antenna setup, how nicely antenna centering and labeling has been done to achieve best accuracy. Then receiver clock, how correctly the receivers are giving time. So these are the common errors. A satellite clock, you can see if 1 billionth of a second of inaccuracy in a satellite clock is there, it will result the error of around 30 centimeter or 1 foot of error in measuring the distance. Second is receiver clock. Assume that at a given time our receiver clock has an error of around 1 millisecond, which causes a distance error of around 3 lakh meters. Error will be there. Then satellite orbital error. The accuracy of the orbital prediction is in the order of a few meters. So if you see here how correctly the orbitals are measured to be of few meters, so this few meters will give 1-to-1 scale error in the output. So this will create about a few meters of error in computing our position through GPS. So you can see overall the error source. Selective availability gives error of around 24 meters. Ionospheric layer gives error of around 7 meters. Tropospheric gives error of around 0.7 meters. Orbital satellite ephemeris gives error of 3.6 meters. Receiver noise gives error of 1.5 meters. So after applying ionospheric model and actual value B, so it is 30 meters. So you can see if we don't apply ionospheric model error or corrections, then the actual error will be around of 30 meters due to ionospheric layer. Same way we are applying topographic error, otherwise topographic error is also to be very high. Tropospheric model, here we can use the delay due to tropospheric layer is equal to 2.47 divided by sin phi plus 0.0121 meters. So this company in this formula, the tropospheric delays depend upon satellite inclination angle or elevation angle. So we should take care the elevation angle of the satellite should be optimum. It should not be very low. If it is low, then the signal length increases while interacting the atmospheric delay. So we should avoid the satellites which are very close to the horizon. Ionospheric error, if you see, we can calculate the delay in the difference in delay in the ionospheric layer is equal to a square of second frequency multiplied by delta delta T1 and divided by F1 square minus F2 square. So F1 is the first frequency and F2 is the second frequency. So from there we can get the delay at frequency 1. Multipath, I've already explained. Let me see through text. In addition to the direct signal, there are reflected signals from the ground and the objects near the antenna, and that also reaches the antenna through indirect path and infer with the direct signal. So there are reflected signals from the ground and from the surrounding objects which create the multipath error. You can see here, this is the direct signal received by the antenna and this is the secondary signal. So this will give the multipath, and here due to high rising object, this signal has been blocked to go to this GPS receiver. And when the signal is blocked, the geometry of the satellite becomes poor. So we should take care the satellite should not get blocked and there should be no multipath problem. If there is multipath, we can go for image processing step, but before that in the ground we can use choke ring antenna. So if we have choke ring antenna here, no, I don't have the image maybe. So choke ring antenna is a concentric circles. It's quite big one and it is triple times costlier. So with the help of choke ring antenna, it can take care the multipath if the signal is secondary signal is received from in the ground itself. But if you want to remove that signal through image processing, so that is also possible. Receiver error. Receivers may introduce some error by themselves in measuring code or carrier in high quality, because this is due to a receiver working for a long time and they get heated up, and once they are heated up they will introduce error in the measuring code or in the carrier. High quality receivers, however, these errors are negligible of millimeters for carrier phase and few centimeters for code phase. So if we have very good, very high quality receivers, they passes through the this receiver based noise coming up, so they take care how to reduce this noise. The sources of inaccuracy and the cures, the error due to the satellite clock, the satellite orbit, ionosphere and the tropospheric and selective availability affect the both receivers and the same way and with the same magnitude. So all these errors gives the same way, affect the same way and with the same magnitude. These errors can be compensated using the technique called differential or relative mode. So here, differential or relative mode, we can decrease these errors. So multipath error, on the other hand, could be as much as several meters for the code phase and several centimeters for the carrier phase, which can be minimized using choke ring antenna. So multipath problem can be handled through choke ring antenna. Here you can see they are the concentric circle antenna, which is triple the size of the survey grade antenna, and its cost also double or triple times in comparison to survey grade antenna. So this is the choke ring antenna. So from this slide, I have talked about the two sections today. One is GNSS receivers and second is GNSS errors. So while doing in the field, once we are aware about the GNSS or GPS errors, we should take care these errors should be as low as possible. Otherwise, our data will have a lot of error and it will create a problem while integrating with other data sets or while processing this data with other remote sensing or GIS database. And I also talked about initially GNSS receivers. With that, I think you got an idea type of GPS receivers we can have. One is geodetic single or dual frequency, Their accuracy is very high, up to millimeter we can achieve, but their cost increases and they have to be used in a pair to work as a base and rover. Then we can have the handheld GPS receiver. The cost is very low, maybe starting nowadays 5,000 to 40,000 or 50,000 depending upon configurations. And we can also have mobile GIS GPS nowadays using app and the GNSS chip in a mobile phone. In a smart mobile phone, we may have the GNSS chip, which can lock the satellites from different constellations. And within few minutes, we can start getting the coordinates and we can apply the high accurate measurements in the data. So with that, the accuracy in the output or in the data what we receive through smart mobile phone using GNSS chip receiver, the accuracy we can achieve to be around 1 to 2 meters. Thank you all. This is all about for today's lecture, and tomorrow the last lecture from my side I will be talking about augmentation, satellite-based augmentation. So that is satellite-based augmentation system, SBAS, and there are different type of segmentations, and I will also talk about Gagan specifically for India and try to understand what's the meaning of segmentation. Thank you all.